I wanted to work through a problem that involves Coulomb's law and also involves superposition principle. And this problem has this arrangement of three charges. There's Q1 over on the bottom left, there's Q2 bottom right, and there's Q3 upstairs. And we're told the exact arrangement of the charges and the values of the charges, and we're asked to figure out the net force or the total force that's exerted on Q1 due to the other two charges, that's Q2 and Q3. And so we're going to go ahead and we're going to solve this problem. As I say, we'll be using Coulomb's law, and we'll be importantly using superposition principle also. So I'm working on this problem. I'm going to start this problem just by adding to the drawing sketch of the arrangement of charges. I'm going to depict on that the forces that are exerted on Q1, and specifically the force on Q1 due to Q2. Now, they're both positive charges, so that's going to be a repulsive force. And here's the force arrow, something like this. And I'm going to label that force arrow F12. It's the force of charge 2 on charge number 1. And then there's a second individual force. That's the force between Q1 and Q3. I'm going to draw that force. Now, those are opposite charges, so that's an attractive force. Here's the force arrow. And I'm going to label that with F13. It's the force of charge 3 on charge number 1. So those are the two individual forces. And they're going to add up to make a net force, a total force. And that's what we want to figure out. If I was to draw it, it might look something like this. So that's the net force. And what I'm drawing is the sum of F12, that's this force on the left, plus F13, this is force on the right. So I could do it by adding 2 F12, F13, or I could do it by adding 2 F13, F12. But anyway, this vector here is the net force. This is ultimately what we want to figure out. Okay, so there's going to be a few steps in figuring this out. The first step I'm going to do is kind of a straightforward step. I'm just going to find the sizes of those two individual forces, F12 and F13. So I'm going to do that step first. Then I'm going to worry about this problem of superposition and adding up the forces. So F12, I'm going to write these upstairs here. The size of F12, and I'm just worrying about the size here, so nothing about the direction, just something about the magnitude, is Coulomb constant times the sizes of the charges So these are the sizes of Q1 and Q2, divided by the square of the distance between them. I'm going to label that distance R. It's the distance between Q1 and Q2. It's also actually the distance between Q1 and Q3, because these charges lie on a equilateral triangle. And so we've got to divide by the square of the separation of those two charges. And if you fill in all the numbers, I already figured this out. I got a force that is 0.504 newtons. And so that's the strength, only the strength of force F12. I can do the same thing for the second force, the interaction between charges 1 and 3. Again, is by Coulomb's law, just the Coulomb constant times the product of the charges divided by the square of the distance between the charges. Again, that's 0.5 meters. And if I fill in those numbers, I already worked this out, I got 0.288 newtons. And so that's the strength of the second force. So now, and this is the big part of this problem, we've got to add up these forces. We've got to apply superposition principle. And so we're going to go ahead and do that. And in this case, because the forces aren't in some simple arrangement, like in the same direction or in opposite directions, I'm going to use a method of adding up these force vectors, which uses the horizontal and vertical components of the vectors, the x and y components of the vectors. So my first task is actually, I'm going to write down what the horizontal component of F12 is and what the horizontal vertical component of F12 is. And then I'm going to do the same thing for F13, what's its horizontal component, and F13Y, its vertical component. And so I'm breaking up the two forces into their x and y horizontal vertical components. So we're going to do that. The way I would do that is to picture on the diagram their horizontal and vertical components. So this side here, that's the horizontal component of force F12. This side here, that's the vertical component of force F12. And this angle here, this is 30 degrees. And so we can use that information to figure out the magnitude of the horizontal component of F12. It's the opposite side of this triangle. So it would be F12, the magnitude of the vector, magnitude of the force, times the sine of that angle, 30 degrees. And if you look on the diagram, you see it's in the negative direction. It's towards the left. I'll put that minus sign in by hand. And then if we want the vertical component of F12, well, the vertical component is adjacent to the angle. So it's F12, the magnitude of the force, cosine 30 degrees. And it also is in the negative direction. It's downwards. So I'll put that minus sign in. So those are equations for the components of the xy components of the first force. Then we want the xy components of the second force. We'll look at that second force. It's going to be easier. It's pointing simply in the positive x direction. There is no vertical components of that force. So F13x, the x component of that force, is simply the size of the force. And F13y, the vertical component of that force, that's simply 0. Okay, so let's fill in the numbers here. F12, that was 0.5 newtons. We've got to multiply it by the sine of 30 degrees. I went ahead and did that. I've got 0.252 newtons and a minus sign because it's in the negative x direction. And then I got F12 again for the y component, 0.5 newtons times cosine of 30 degrees. I calculated that to be 0.437 newtons, and that is also in the negative direction. And then finally, for F13x component, the x component of the second force, that's simply equal to the magnitude of the second force, 0.288 newtons. Okay, so that's a big step. I'm going to label that step 1 maybe, in our adding up of the two forces. We've broken the two forces down into their horizontal vector components. Now the second step then, in finding the total force, is to find the components of the total force. So we're going to find Fx and Fy, the horizontal and vertical components of the net force. That's the force here on our diagram. And Fx is simply the simple sum, simple addition of the two x components of the two forces. So F12x plus F13x. And Fy, again, simply the simple sum, arithmetic sum of the two y components of the two forces. And so if we fill in the numbers and calculate the x and y components of the resulting force, for the x component, I'm going to get 0.25 newtons minus 0.25 newtons plus 0.288 newtons. That comes out to be, they almost cancel out, but not quite. There's a small x component in the positive x direction. And then for the y components, well, the y component of the first vector is minus 0.437 newtons, but there's no component of the second vector in the y direction. So this is just 0.437 newtons. And so that's the second step. And really we have the force, the resulting force, the net force calculated here, but it's just in this x and y component language. Our third step is that I'm going to calculate the magnitude and the direction of the force. So that's a very final thing I'm going to do. For the magnitude, I'm going to use Pythagoras' theorem, which applies to right-angled triangles. And the x and y components and the magnitude form a right-angled triangle. And then I'm going to use the inverse tangent or arctangent to find the direction. And let me draw a little picture to go with those pairs of equations. So here is F, and here is Fx, its x component, and here's its y component. Now, I haven't drawn this to scale, but I wanted to show you the relationship really just between the magnitude of the force and the x and the y components of the force. So F is the hypotenuse of this right-angled triangle. And so this first equation is the relationship between the horizontal and vertical sides in the hypotenuse. And then this second equation, what I'm going to be doing is calculating this angle here in the triangle. And I'm going to be calculating it from the ratio of the sizes of the vertical component and the horizontal component of the force. And that will tell me this number of degrees. It will tell me this angle here. So this is just tan theta equals opposite over adjacent, and applying that tan theta to this particular triangle and thinking about this particular angle. Okay, so let's do the calculation now. If I fill in the x and y components here, I'm going to have the square root of 0.036 newton squared plus minus 0.437 newtons squared. Since the x component is much smaller than the y component, actually the magnitude of the force is barely bigger than the y component of the force. And when I did this calculation, it came out to be 0.438 newtons. So that's the magnitude of the force. And then the direction of the force, again, I'm looking at this right angle triangle here. I'm going to take the ratio of the magnitude of the y to the x component. So don't worry about the signs when I'm using this equation here, just the sizes of these two components. And I take the inverse tangent of that, and I got 85.3 degrees. And that's that angle in here. And it's nearly 90 degrees because actually fx is quite small and fy is much bigger. Anyway, I wanted to show that as an example of Coulomb's law. But in this problem, I say more importantly, the superposition principle. Coulomb's law is just the force between a pair of point charges. To solve more complicated problems where we had several charges in this problem, you need to supplement it with superposition principle, which simply says that the resulting force, the total force, net force, is the sum of all the individual forces acting on a particular charge. And in this problem, we use this technique of breaking down, disassembling forces into their x and y components to do the addition, the summing of those force vectors. So most of our work was really handling force vectors and handling the addition of force vectors.